Hi, I'm Michael Taylor from the Coolert Group at MIT, and thank you for attending my pre-recorded AIChE talk, where I'll be discussing leveraging experimental transition metal complex information to improve generalizability of machine learning models. In this case, we'll largely be focusing on artificial neural networks. So what are transition metal complexes? These are transition metal ions, or in this case, I'm showing iron surrounded by a ligand field in sort of a heterogeneous complex where these are used in applications from optical devices to catalysis. And one of the properties of these, especially open shell transition metal complexes that our group has focused largely on is focusing on spin state energetics, where a complex in the center might have a low spin state where all of the electrons in the ground state are paired, whereas the complex on the right, maybe it has a different ligand field or a different temperature, forms many more unpaired electrons in its ground state and is therefore called a high spin, and potentially shows different bond lengths or bond length information, which can have a dramatic influence on the catalytic properties of the complexes themselves. So the most widely applied theoretical method for understanding these complexes is density functional theory, which has been successfully applied to this complex design and discovery. However, for this spin state determinations, especially in terms of energetics, we see that density functional theory can actually show a large degree of sensitivity to density functional, where across a wide range of different ligands and simple homoleptic octahedral complexes, we see that there can actually be a wide variety of energetics that are observed for even just varying the Hartree-Fock exchange percentage within the density functional, where it can actually change the ground state versus the ground state a spin of either high spin versus low spin. So for a larger data set or potentially more diverse structural data, this might present an issue. So we're wondering how large and how diverse is this data? Will you turn to the experimental data source from the Cambridge Structural Database, the largest repository of different complexes, transition metal complexes available. And if we look over this set, we see that there's a wide variety of oxidation states, including about 9 different oxidation states for simply first row transition metals, where we're from chromium to nickel. And for cobalt and iron, we note that there are almost there are almost more than 10,000 complexes present. Then if we look at the actual sample of structures that are from this data set, we see that there are a wide variety of ligand symmetries, sizes, shapes, so much more complicated than the simple homoleptic complexes for which we saw spin state. So we saw the spin state dependent energetics. And largely, these are unlabeled with spin states. So they're experimentally reported, and even potentially the authors don't know what the actual spin states of the complexes are for especially complexes that are not Mossbauer active. For example, complexes that are not iron, which you cannot, it's not easily readily experimentally determine what their spin state is. So there's an important property here that the ground spin state cannot be, it's difficult to determine with experiments, even with density functional theory, where we see this high sensitivity. However, interestingly, we've noted previously that for the same variation within the functional, so the same variation of Hartree-Fock exchange percentage, we see that the bond lengths vary quite a bit less over the same ligand field, where the high spin versus the low spin, we see that the shaded regions on the plot show much less variation for bond length than they do for the actual energetics of the difference between the spin states. Additionally, we have previously trained artificial neural network models to accurately predict density functional theory derived metal ligand bond lengths. So combining all this information together, we'd like to develop rapid and accurate method for classifying ground spin states in experimental structures. In particular, we're interested in focusing towards catalytic properties. So how are we going to represent these models and train artificial neural networks on these? We're going to leverage featurizations that have been developed in the Coolert group over the years, including called revised autocorrelations, which represent the products and differences on the molecular graph of chemically intuitive properties such as the nuclear charge, the covalent radii, the topology, the identity, and the Pauling electronegativity. So this would be graph-derived featurizations. So we can take these at multiple different scopes. So we can look at the metal-centered or the ligand-centered or the global properties. And for this work, we're particularly interested in axial versus equatorial, where we see there can be differences in bonding and bond lengths in the axial and equatorial planes. And we can also take these at various depths. So for example, the metal-centered racks can be taken to depth 1. So we take the product and differences of these properties between the metal center and its first nearest neighbor, second nearest neighbor, third nearest neighbor. So if we take all of these various scopes, properties, and depths, we were able to get 155 total connectivity only descriptors. So we're not actually feeding any geometric information or bond length information into the model. So we're able to predict from simple graph-based descriptors and chemistry-based properties. We're able to predict things like bond lengths. So the models that we're using are ANN models. They're trained on about 1,000, around 1,000. B3-LIP, LACVP star density functional theory results that are on quite equatorially symmetric and procedurally generated complexes. So a lot of these are actually monodentate and that have been evaluated with DFT and TerraChem. So the ANNs themselves have a quite large architecture. So they have 3 hidden layers with 300 by 300 by 200 hidden nodes. They have hyperbolic tangent activation and about a 5% dropout rate to improve the generalizability and learning across diverse chemistries. All of these hyperparameters were changed from HyperOpt. So I'd also note that these are multitask ANNs, so we're training these on both the axial and equatorial bond lengths of these complexes, and we're using about an 80-20 train validate split. So to find and track down experimentally relevant complexes for which we be able to determine what the ground state spin is, we want to pull out all that we can from the CSD. So we're going to mine all the iron complexes that have 6 bond lengths with roughly octahedral angles, which is about 13,000 complexes. We filter out multi-metal complexes and complexes that show different differences in bonding. We get about 5,000 complexes. If we filter out structural duplicates, we actually get about 3,500 unique octahedral complexes or chemically distinct octahedral complexes. And then if we further constrain the equatorial symmetry to be similar to what the ANN was trained on, where we have the same atoms that are connecting in the equatorial plane and roughly similar bond lengths, we're able to get about 2,000 ANN compatible complexes. So if we look at this set, we wanted to see, do we need more complicated methods? Do we need ANNs? Or can we simply do this with something like a normalized bond length? If we look at the normalized bond lengths over especially symmetric complexes, we see that, especially focusing on nitrogen, that there is a sense in which there's bimodal distributions in terms of the normalized bond lengths between the iron metal center and the ligands. However, we see that there is also significant overlap even for nitrogen. Whereas for some of these, including carbon and oxygen, connecting atom complexes, there's no bimodal distribution, and determining between what is low spin and high spin might prove very difficult over the set. So bond length heuristics cannot uniformly distinguish the spin states, so we need to potentially see if there's something we can use with the generalization of our ANN to this more complex experimental data set. So to compare the ANN and generalize it to this data set, what we did is we calculated a simple RMSD, or difference between the bond lengths that are predicted by the ANN and the actual experimental CSD bond lengths. And we weighted it by the number of bonds that are present in each, so to get an RMSD metric. We also created a basic metric for uncertainty that would be how different is the experiment from the ANN versus how different is the high spin ANN from the low spin ANN. And if we look at the uncertainty score over all of these, this uncertainty over the whole data set, we see that there's a nice distribution here, and there's actually a fair number of these for which we have a very low degree of uncertainty, or the complex is being predicted quite accurately by the ANN. If we put this to numbers, we see that we classify about 78% of all of these complexes with some degree of certainty. We see that especially for the complexes for which we have a high degree of a high degree of certainty, we're actually able to get pretty good visually inspect. We see we're able to get pretty good prediction of the actual bond lengths, which is surprising considering the ANN is trained on DFT and we're comparing to now experimental bond lengths. And we see that there is actually an overlap between the distributions of the low spin bond lengths and the high spin bond lengths, and these are complexes for which we're saying we have a high degree of certainty. Additionally, if we highlight some cases that would be especially ambiguous, so things that would be in the middle of the sort of bimodal distribution, especially for nitrogen here, we highlight that we're able to classify correctly both the low spin on the left complex, where it's much, we can see that the CSD bond lengths are much closer to the ANN low spin bond lengths. This is actually correctly classified as low spin, whereas the high spin complex on the right is also really intermediate between what would be heuristic cutoffs for low spin and high spin, and is quite close to the high spin ANN bond length and is predicted correctly. So to further extend and curate this set, what we've done is we've found additional experimental data that's for which we can know the spin state, and these are from spin crossover complexes, or complexes that are low spin with low temperature and high spin with high temperature, identified from the CSD. So what we did for this is we pulled out the abstracts of all the papers that these complexes came from and said, are they discussing spin crossover, and are they talking about this with a positive text sentiment in terms of Vader? And then in the CSD, in terms of the data, have they have the people who reported these structures actually measured them at multiple different temperatures in crystallography and reported the structures in the CSD. And we see that this turns out a data set of about 46 complexes that have been measured at both high and low temperature. And we use this to compare to our ANN. And we see in the complex, in the figure on the left, that there's actually fairly good prediction, especially for the low spin state compared to the low spin to the low temperature XRD. And these are all iron nitrogen complexes. And so if we put the similar sort of thing to our RMSD, where we just take the absolute difference of are the bond lengths that are predicted closer to the high spin ANN, or are they bond lengths that are predicted closer to the low spin ANN, we see that we're able to classify to a large degree the high temperature structures as high spin and the low temperature structures as low spin, with only 4 complexes being misclassified, which is about a 96% accuracy over this sort of SEO data set. However, we're also interested in can we actually improve this prediction by including some sampled or targeted sampled experimental data that's actually very different from the SEO complexes. So for this, we pulled out and randomly sampled from the CSD sort of ANN compatible CSD complexes that are from chromium all the way to nickel. And if we include this 220 additional data set, we actually see that if we retrain the ANN with all of this additional data, we get actually a little bit worse separation, or we get worse bond length predictions. But we do actually see a separation between the distributions. And so this said that this told us that there's potentially too much diversity that we're introducing too fast compared to the very highly symmetric initial training data. So if we reduce the amount of data that we're introducing and we do a 50% random additional sample of this already randomly sampled CSD complexes, we see that we're able to actually improve the prediction. So we see that there's only 2 complexes that are predicted incorrectly in terms of high spin versus low spin ground state. And additionally, if we choose a different sampling strategy, if we pick the most uncertain complexes, or that the ANN would be initially most uncertain on, and we retrain the ANN with these most uncertain complexes at the same amount of data, we're actually able to get 100% distinguishing between the high spin and the low spin cases over the SEO complex data set. So in conclusion, we showed that bond length can be valuable in determining ground state spin. We generalized the DFT trained ANN to predict experimental spin states where heuristic bond length even fails. We predicted spin of iron 2 SEO complexes with 96% accuracy, and we reinforced the ANN even more experimental data for even more accurate predictions. So with that, I'd like to thank the Kulik group at MIT, especially Professor Kulik, for all of her advice and help. The inorganic subgroup, including especially Aditya, Daniel, Naveen, and Chenru, are funding sources. And I'd like to thank you for listening to my talk, and I'd be happy to take any questions.